Welcome back to the deep dive. Today we are opening up a topic that I think most of us use literally every single day, probably without giving it a second thought. We're talking about the voice in your phone, the GPS telling you to turn left, the screen reader. We are talking about text-to-speech synthesis.
It's funny because it feels like such a mundane utility now, right?
Yeah.
You type something, the machine says it.
Yeah, problem solved.
But if you actually look at the history and the math behind it, it is arguably one of those difficult engineering challenges humans have ever tried to solve.
And the source material, right off the bat, it throws this term at us that I just loved. It calls text-to-speech an ill-posed problem.
Yeah, that's a perfect place to start.
What does that even mean?
Well, in mathematics, a well-posed problem has one and only one unique solution. Like 2 + 2 = 4.
No debate.
There's no debate. But an ill-posed problem, that means there isn't one single right answer.
Which makes total sense for speech. If I give you the text, hello, how are you? There's not just one way to say that.
Exactly. You could whisper it, you could shout it, you could say it with a sarcastic lilt or, I don't know, with a thick Scottish accent. All of those are correct acoustic solutions to that one text string.
Right.
So the computer doesn't just have to find an answer, it has to pick the best answer out of basically an infinite number of possibilities.
But here's the kicker, and the sources make a really big deal out of this. While there are a million right ways to say it, there are infinitely more ways to say it wrong.
That's the cruelty of the problem. Human listeners have basically zero tolerance for error.
Zero.
We've evolved over millions of years to detect nuance in voices. If the rhythm is off by a millisecond or the pitch is just slightly too flat, our brains immediately flag it. We recoil. It just sounds wrong.
So the mission of this deep dive, really, is to trace how we went from what? Mechanical bellow?
Literal bags of air.
Literal bags of air to the deep neural networks we have today. And to understand why this was such a struggle, we have to talk about information theory.
This is one of my favorite parts of the research. It frames speech not just as sound, but as bandwidth.
Right. It compares the bandwidth of text versus the bandwidth of speech. And the gap it's massive.
It's huge. Think of text as narrow band. It's highly compressed. You can convey a lot of meaning with just a few bytes of ASCII characters.
Sure.
But speech is wide band. The research puts the information rate of human speech at roughly 50 bits per second.
50 bits per second. Now, in the age of gigabit fiber internet, that sounds tiny.
For a computer transferring a file, of course. But for a biological interface, it is staggering.
Okay.
That 50 bits per second represents about 10 distinct phonemes, 10 individual sounds being dropped every single second.
And the comparison they gave really drove this home for me. They compared it to brain-computer interfaces.
Right. So if you look at people trying to control a cursor with their mind, using a brain implant, those systems struggle to hit 20 or 30 bits per minute.
Per minute.
Meanwhile, your mouth is firing off 50 bits per second.
So speech is basically a motor control fire hose.
It is the fastest discrete motor output the human body is capable of. And we're trying to build machines that can replicate that fire hose with zero latency, perfect accuracy, and this is the new frontier emotional expressivity.
Okay, so let's unpack how we actually try to build this. Because when I first started reading this, my naive brain went to the most obvious solution. I call it the ransom note approach.
I think everyone starts there.
Right. Why not just record a human reading the dictionary? You record the word apple, you record the word is, you record red, then you just cut and paste them together. Apple is red, boom, speech.
It makes perfect logical sense, but it fails miserably. And it fails because of something called the cut and paste fallacy.
Which boils down to two main things, prosody and co-articulation. Let's start with prosody. That's the melody, right? The music.
Correct. Prosody is the pitch, the duration, the stress. A word isn't a static brick. It's flexible. The word apple sounds completely different depending on where it sits in a sentence.
Can you give me an example?
Okay. If you say, that is an apple, your pitch drops at the end. It signals a statement.
Right.
But if you say, is that an apple, your pitch rises on the exact same word. If you took the recording from the statement and pasted it into the question, it would sound jarring. It would sound like an automated phone menu from 1995.
Please listen carefully.
Exactly. But honestly, prosody is the easier problem.
Yeah.
The real nightmare, the thing that makes the cut and paste method physically impossible, is co-articulation.
This was the concept that really blew my mind. We tend to think of speech as a string of beads. Sound A, then sound B, then sound C.
But it's not beats. It's a fluid stream.
Hmm.
We don't produce sounds independently. Our mouth muscles they're sluggish. They're always moving from one position to the next, and they anticipate what's coming.
The source material used a French example that I thought was brilliant. The words annuel and actual.
Yes. So annual, which is annual, and actual, which is current. Both words end with the sound U.
Okay.
On paper, phonetically, that ending is identical.
So you should be able to just swap them.
You'd think. But in reality, you can't. In the word annual, the sound before the U is N. In actual, the sound before is T.
And that one preceding letter changes the U?
Completely in actual, because your tongue is blocked against your teeth to make that T sound, your vocal cords haven't fully started vibrating when you slide into the U. It creates a different resonance. This is called backward co-articulation. Your mouth is physically shaping the U differently because of where it just came from.
So if I took the UL recording from annual and pasted it onto act, it wouldn't just sound like a bad edit. It would sound physically impossible.
It would sound like you grew a second mouth for a millisecond. The human ear picks up on those physical discontinuities instantly. We hate gaps, and we hate physics violations in sound.
So cut and paste is out. To actually build a voice, you need a more complex architecture. The research breaks this down into two main brains.
Right. Whether it's 1980 or 2024, the architecture usually splits into two parts. First, you have the NLP module natural language processing.
The brain.
Think of that as the brain that reads the text. And then the second part,
The vocal cords.
the DSP module digital signal processing. That's the vocal cords that actually generates the noise.
Let's look at the brain part first, because you might think reading text is easy. I mean, we do it all the time. But for a computer, text is a minefield.
It is full of traps. Take abbreviations. You see the string, Saint.
Right, could be street or saint.
St. John lives on St. John Saint.
Exactly. A human reads that effortlessly. We know the first one's a title, the second's a name, and the third is a place. The NLP module has to parse the context to figure that out. If it gets it wrong, intelligibility just breaks.
Or homographs. Words spelled the same but pronounced differently.
I need to record a new record.
Perfect. Noun versus verb. The stress shifts from the second syllable to the first. The NLP brain has to tag that correctly before it even sends instructions to the vocal cords.
And this brings us to the dreaded uncanny valley.
Oh, yes.
We talk about this in robotics. If a robot looks almost human but, doesn't blink right, it's creepy, but it applies to voice too.
Absolutely. In fact, it might be worse with voice. If a voice sounds like a Dalek from Doctor Who, totally robotic, we accept it. It's a machine.
Right.
But as the quality gets better, if it sounds human but has a weird metallic buzz or a flat rhythm, it triggers a revulsion response. It sounds like a sick person or a zombie.
So the history of TTS is basically us trying to cross this valley without falling in. And the timeline it's wild. We start way back in the 18th century.
Evolution Era 1, the mechanical origins, and this wasn't software, this was pure hardware. Wolfgang von Kempelen in 1791.
I looked at the diagrams for this machine. It is incredibly steampunk. It looks like a bagpipe had a baby with a bellows.
It really does. Use a bellows to pump air acting as lungs. A vibrating reed acted as the vocal cords. And a leather cup acted as the mouth.
And it even had nostrils.
It did. Small auxiliary pipes to simulate the nasal cavity. And the crazy thing is, you had to play it. You squeezed the bellows with your elbow, and you manipulated the leather cup with your hands to shape the vowels.
So it wasn't automated at all. It was a puppet.
A vocal puppet. A trained operator could produce about 20 recognizable sounds.
No.
But it proved a point. Speech was just physics. If you could replicate the airflow, you could make the sound.
Which brings us to the 20th century, 1939, the voder.
The first electrical synthesizer. They showed it off at the World's Fair. But again, this wasn't a computer program. It was an instrument.
It looked like a weird organ with a wrist bar.
Right. 10 keys controlled filters to shape the tone. A wrist bar switched between a buzz, the voice sound, and a hiss, the whisper sound, and then a foot pedal controlled pitch.
So to say hello, you had to perform this complex dance of wrist, fingers, and feet.
It took a year of training to get good at it. The operators were usually these incredibly skilled telephone switchboard operators.
Wow.
But the key takeaway here is that the intelligence was still human. The machine was just the vocal cords. The human was the brain.
So when do we actually get the computer to do the thinking? That brings us to Evolution Era 2, the battle between rules and data.
This starts in the 60s and 70s with synthesis by rule. This is what we call format synthesis.
Think of the original Stephen Hawking voice.
That's it. That classic monotonic hello world sound.
Yeah.
That voice wasn't made from recordings, it was made from code. Linguists wrote explicit rules. If you have an S followed by an ah, set the frequency to X and the duration to Y.
So it's like painting by numbers or sketching a face with a pencil. It was highly intelligible, very clear, but completely unnatural. It lacked the texture of a real voice because it was just a mathematical approximation of sound waves. It was a sketch, not a photo.
But because it was just math, it was tiny. You could fit it on a cheap chip. Tiny and fast. But people hated listening to it for long periods. It was fatiguing. So in the 80s and 90s, the pendulum swung the other way. We moved to concatenative synthesis.
This sounds like we're going back to the ransom note idea.
We are, but with a clever twist. They realized the cut-and-paste fallacy was real, so they couldn't cut at the edges of words. So they invented the diphone.
A diphone.
Instead of cutting from the start of a sound to the end, you cut from the middle of one sound to the middle of the next.
Wait, why the middle?
Because the middle of a sound, like the center of an ah, is stable. The edges are where all the action happens, where the mouth is moving and co-articulating.
Oh. Okay.
By cutting in the middle, you capture that messy transition intact inside the recording. You glue the stable parts together.
That is actually really clever. You aren't building the transition, you are recording the transition.
Precisely. And this evolved into unit selection in the 90s. The philosophy became, don't generate fake audio. Just take the best chunk of real audio from a massive database and modify it as little as possible.
But this is where we run into a problem called Zipf's law.
Ah, Zipf's law, the nemesis of early AI.
Break it down for us.
In language, Zipf's law essentially says that a few words are used constantly, but there's a long tail of millions of rare combinations.
Meaning?
Meaning that no matter how much you record, you will never capture every possible combination of sounds, pitches, and speeds. To cover just 75% of a random sentence with high-quality units, you need roughly 150,000 different chunks.
Wow.
That's about 5 hours of recorded speech.
And back in the 90s, storing hundreds of megabytes was a huge deal.
It was huge. And the problem was, if you didn't have the exact right chunk, the system would have to grab a close enough chunk, and you'd get a glitch.
Right.
The voice would suddenly pitch shift or sound like a...
Like a different person for a split second.
Exactly. So it sounded great when it worked, but when it failed, it broke the illusion completely.
Okay, so we needed something that had the smoothness of the rule-based systems, but the quality of the recorded systems.
Enter Era 3, Statistical Parametric Synthesis.
Or HMMs. Hidden Markov models. This feels like the bridge to the modern era.
It was a huge paradigm shift. The idea was, instead of storing the actual heavy audio clips, what if we just store the statistics of the audio?
How do you store the statistics of a sound?
Imagine a face again. Instead of keeping a high-res photo, which is the concatenative approach, I keep a mathematical formula that describes the curvature of the nose, the distance between the eyes, the texture of the skin.
I see.
HMMs used Gaussian models to predict what the speech should sound like based on the data.
So it's generating the sound from scratch, like the old robot voices, but based on a model of a real human.
Yes, and the benefits were massive. The footprint went from hundreds of megabytes down to just 1 megabyte. You could fit a voice on a flip phone in 2005, and it was fluid. No glitches, because it was generating a continuous wave.
But there's a catch. I remember those early GPS voices. They didn't glitch, but they sounded muffled.
The industry term is over-smoothed. Because HMMs work on averages, they tend to average out all the crisp details. It sounds like the person is speaking through a heavy curtain or has a slight cold. It lost that sparkle.
But the source mentions a really cool capability of HMM as voice morphing.
Yes. Because it's just math parameters, you can tweak them. You can shift to the average pitch to change the gender. You could even take a model of a generic voice, feed it 5 minutes of your voice, and adapt the model to sound like you.
Which you just couldn't do with the cut and paste method. You'd need to record the whole database again.
Exactly.
So we had the robot sketch from the rules, the ransom note from unit selection, and now the muffled math from HMMs. We're stuck in this trade-off triangle. And then 2016 happens.
The modern era. Deep learning comes in and flips the entire table.
This is where we start seeing terms like waveform, and this is where the computational power really flexes its muscles.
Waveform changed the game completely. It was a deep neural network developed by DeepMind. And it didn't use the old vocoders or simplified models. It generated the raw audio waveform, sample by sample.
I want to pause on sample by sample, because audio is usually sampled at, what, 16,000 times a second?
At least. often 24,000 or even 44,000.
Uh,
WaveNet wasn't predicting words. It was predicting the voltage value of every single one of those tiny slices
yeah.
based on the thousands of slices that came before it.
That sounds incredibly computationally expensive.
It was. The original version took minutes just to generate 1 second of audio. You couldn't run it on a phone.
No way.
But the result, it was stunning. It sounded natural. The buzziness was gone. The glitches were gone. It closed the gap between human and machine performance by about 50% in one shot.
And then came Talkatron, which sounds like a transformer, but it plays a different role.
Talkatron represents the end-to-end shift. This is the black box era.
Yeah.
Before this, we had linguists writing rules, defining phones, teaching the computer how to pronounce record versus record. Talkatron's concept is, here are the text characters, here's the audio. You figure it out.
It skips the linguists.
It learns the rules from the data. It's character to speech. The neural network maps the letters directly to the acoustic properties.
That reminds me of that quote in the research from Frederick Jelinek at IBM. It's from the 90s, but it seems so prophetic now.
A classic and slightly ruthless quote. Each time I fire a linguist, the recognition rate goes up 1%.
Ouch.
It's harsh, but it captures the trend. We moved from understanding how speech works, building models of the vocal tract, to building machines that figured out themselves from massive amounts of data. We replaced human expertise with machine learning.
So looking at where we are now, we've gone from von Kempelen's leather bellows to neural networks that generate raw waveforms. What's left?
The next frontier is perfect prosody in conversational speech.
Conversational. Because my smart speaker still sounds like it's reading a Wikipedia article.
Exactly. Right now, most TTS is read speech. It's very proper.
Yeah.
But real conversation is messy. We hesitate. We say, and we speed up when we're excited. We interrupt ourselves.
We laugh while talking.
Right. Making a machine sound like it's thinking while it speaks, rather than just reading a pre-generated script, that's the next big hurdle. And connected to that is emotion.
And not just sad or happy.
No, subtle things. Sarcasm, uncertainty, empathy. I'm sorry, I can't do that. Sounds very different depending on whether the speaker is actually sorry or just following a protocol. Modeling those subtextual layers is incredibly hard because they depend on deep context, understanding the world, not just the text.
So what does this all mean for us? We have reached a point where the machine voice is effectively indistinguishable from the human voice, at least for short bursts.
We have. And I want to leave you with a thought that the research touches on. It's a bit of a paradox.
Let's hear it.
To achieve this perfection, we had to give up understanding. When we used the rule-based systems, we knew exactly why the computer sounded the way it did. We had a model of the vocal tract. We were the architects.
We could look at the code and say, line 40 sets the pitch.
Right. But with these deep learning end-to-end systems, they are black boxes. We feed in text, we get out perfect speech, but the internal logic, the how, is distributed across millions of neural weights.
So
We have achieved near-perfect synthetic speech by removing human speech science from the loop.
that is slightly unsettling. We built a machine that understands how to speak better than we understand how it speaks.
Precisely. We traded control for quality. And as these systems start handling our news, our customer service, even our therapy, it's worth asking if we are comfortable with that trade-off.
A black box that speaks with our voice. Something to mull over the next time you ask your phone for the weather.
Thanks for listening to this deep dive into text-to-speech.
It's a pleasure.
See you next time.